Today's lesson is on applying the sine and cosine graphs. So sine and cosine graphs are pretty useful to model situations that are periodic in nature. So the first one we're going to look at is a predator-prey situation. The number of animals in each category tends to vary periodically. A certain region has pumas as predators and deer as prey. The number of pumas varies with time according to this function, so 500 plus 200 sine 0.4t minus 0.8, the deer from this equation. So what are the maximum and minimum number of deer? So we're looking at this equation here, and we know from our graphing lessons that we have a vertical shift here of 1,500 and an amplitude of 400. So my midline would be at 1,500, and then we'd go 400 above that and 400 below that. So the maximum is going to be the 1,500 plus 400. The minimum is going to be the 1,500 minus 400. We'll do the same thing with the pumas. So the maximum will be 700. The minimum will be 300. I'm going to go ahead and graph this on the calculator. To graph this, we need to be in radian mode. So make sure that your calculator is in radians. Then we're going to type the two equations just as you see them on your paper. So we have the two equations typed into the calculator. The next thing we need to consider is the window. So if we go to the window, on our x-axis is going to be time. So I'm going to go from maybe 20 years, something like that. So we go from 0 to 20 because we don't care about negative time. For my y values, we've already established some of the values that we're going to get. So the minimum number I'm going to see on my graph is 300. The maximum number I'm going to see on my graph is 1900. So my window needs to account for that. So I'm going to go from we'll just go from 0 to maybe 2,000. And we'll graph. So that top one is our deer population. And there's our puma population. So you can make a sketch of this on your notes there, but let's look at what's happening. So this is the deer population, this is the puma population. So as the deer population is increasing, and this is actually answering this last question, as this is increasing, well, the puma population is going to increase. But as soon as the pumas start increasing, well, the deer population is going to start going down because they're getting eaten. But then as this goes down, then this is going to start going down because there's less, food. Then as this goes down, this is going to start picking back up because they're not getting eaten as much. So that's the relationship here between these two. So you can sketch the graph for how many deer and pumas there will be in 15 years. We can go to our graph and just trace to 15. So for the deer population, there will be 1,388, and we'll just round to the nearest whole number. For the pumas, again, trace to 15. We get 323. In how many years to the nearest tenth does the first maximum number of pumas occur? Okay, so pumas is on this bottom graph. So we're interested in this point right here. So I'm going to calculate a maximum. We're going to do that on this second curve here. It asks us for a left bound, then a right bound, then a guess. So we go to the left of the max, we go to the right of the max, and then we guess. Gives us about 5.9 years. Okay, and again, we've already talked about why they vary there, so you can fill in whatever you want for your own notes. All right, for our next one. Kayla is jumping rope and it touches the ground every time she jumps. She jumps at a rate of 40 jumps per minute. The distance from the ground to the midpoint of the rope is 5 feet at its highest. Sketch a graph and write the equation with a phase shift of 0, which would describe the height of the midpoint of the rope after t seconds. So the midpoint of the rope, here's my drawing. She's holding on to a jump rope. Okay, the middle of the rope is what's going to be at the highest or at the lowest. Okay, so let's sketch ourselves a graph. So we have time and we have the height of the rope. Okay, at its highest, the rope is 5 feet. Its initial height is 0, so it's going to start on the ground, it's going to go up to 5, and then it's going to come back down. What we don't know is how long it takes to complete one cycle. What we have is 40 jumps in 1 minute, which is going to equal 40 jumps in 60 seconds. Okay, this is what's called a frequency. A frequency is the number of cycles in a set amount of time. Period is the time it takes for one cycle. So just as a side note, period is equal to the reciprocal of frequency, and frequency is the reciprocal of period. So we have a frequency, we want a period, so we're going to flip this over. So it takes 40 jumps in 1 second, which means it's going to take 60 seconds to do 40 jumps. Then if we just do that division, 60 divided by 40 is going to be 1.5 seconds per jump. So that's going to be 1.5. From here, we need to fill in the information in our equation. So our amplitude, A, is going to be the distance from the midline to the max to the min. The midline in this case is going to be right here. So my amplitude on this one is going to be 2.5, because from the midline up we go 2.5, from the midline down we go 2.5. The period is 1.5, which means my B is going to be 2 pi divided by 1.5, and I'm just going to leave it like that. Okay. There is no phase shift. We don't want a phase shift, but there is going to be a vertical shift of 2.5. So let's put this in our equation. The next thing we want to do is figure out what trig function would be modeled by this. Well, we have our midline here. If we're starting at the minimum, that's going to be a negative cosine curve. So we're going to have y equals negative 2.5 is my amplitude, cosine, my b is 2 pi over 1.5, and I'm going to use t as my variable. We have no phase shift, plus a vertical shift of 2.5. So all we need to do is just try to gather the information to write the equation of our sine or cosine curve. Okay, Ken observes a buoy at the equilibrium point of a wave bobbing up and down a total distance of 10 feet. The buoy completes one full cycle every 12 seconds. Sketch a graph and write the equation that models the position's height from the equilibrium point. So this one, the wave is at the equilibrium point. It's going to go up, it's going to come back down, and it's going to go there. So negatives actually make sense, because if you think about water, the water is going to be level, and the wave is either going to go above that point or below that point. So to label the points on my graph here, it goes up and down a total distance of 10 feet. So that's going to make that 5 and that negative 5. And it takes 12 seconds to complete a full cycle. So my amplitude is going to be 5. My period is 12, which means my B is going to be 2 pi divided by 12, or pi over 6. We don't have a vertical shift or a phase shift here if we use a sine curve. So this equation is going to be y equals 5 sine pi over 6 times t. Okay, Ferris wheels are another thing that can be represented with a sine or cosine function because it's another thing that's periodic. So a Ferris wheel 50 feet in diameter makes 1 revolution every 40 seconds. If the center of the wheel is 30 feet above the ground, find the equation that models the rider's distance off the ground after t seconds. So we'll go ahead and sketch a graph. Okay, it's going to take us 40 seconds to complete 1 cycle. Let's think about our y distances here. The center of the wheel is going to be at 30, and if the diameter is 50, we're going to go 25 above that and 25 below that. So the height initially is going to be 5 feet. The wheel isn't on the ground, it's 5 feet up. So it's going to go up and then back down here. Okay, so let's gather our pieces of information. Our amplitude is going to be the distance from the midline up or midline back, which is going to be 25. Our period is 40, which means my b is 2 pi over 40, or pi over 20. There's not a phase shift if we do the right trig function. There is a vertical shift of 5. So what trig function would we choose to not have a phase shift? This again is going to be a negative cosine again. So if we put all of this into our equation, we're going to have y equals negative 25. Sorry, our vertical shift is 30. The vertical shift and the midline are always going to be the same, so I apologize. The midline is 30. This is a cosine. Pi over 20t, close parentheses, plus our vertical shift of 30. So how far off the ground is the rider after 15 seconds? You'll plug 15 into here. Make sure your calculator is again in radians. So this would be 47.7 feet when you plug that in, which should make sense because if this is 40, this is 20. So at 15, you're about here on our curve. Then it says, when during the rotation is the rider 50 feet above the ground? Now you can use the calculator to solve this, or we can do this algebraically. So I'm going to set my equation equal to 50. Okay, so algebraically, I'm going to subtract 30. I'm going to divide by 25, negative 25. And you can reduce that, but I'm just going to leave it like that for now. Okay, then algebraically, to undo cosine, we need to use inverses. So I'm going to go over here. So we're going to do cosine inverse of negative 20 over 25 equals pi over 20t. So t, I'll multiply by the reciprocal there, is going to be 20 over pi cosine inverse negative 20 over 25. So we type all of that in the calculator, and you're going to get 15.9 seconds. Okay, but it says when during the first rotation is the rider 50 feet above the ground? Well, if I look at my graph, we're 50 here, which is going to be the 15.9, but we're also 50 when we're coming back down on the other side of the wheel. So how do we find that? Well, we have this is 15.9. What I want to do is find this one. So if we understand the symmetry, the distance from here to here is going to be the distance from here to here. So 20 minus 15.9 is 4.1. So if this distance is 4.1, this distance is 4.1. So my other time is going to be 24.1 seconds. Sound waves are another thing that can be modeled by sine and cosine curves. So a piano tuner strikes a tuning fork for the note middle C and creates a sound wave that can be modeled by 1.5 sine, 524 pi t, where t is time in seconds. So the graph here, I'm actually going to answer this question first. What is the period of the function? So the period is going to be 2 pi divided by 524 pi, that coefficient there. So when we reduce, this is 1 over 262. So that's how many seconds it takes for one cycle. Okay, it takes 1/262nd of a second to cycle through. So for my graph, we have an amplitude of 1.5. This out here is going to be 1 over 262. Okay. And you can label those other ones if you want to. I'm just going to leave them. So we're going to start at the bottom because it's a sine. Okay, so the period is 1 over 262. The frequency, again, is going to be the reciprocal of the period. So if the period is 1 over 262, my frequency is going to be 262 cycles per second, which has its own name of hertz. Okay, another thing that can be modeled with a periodic function is temperatures. So we have the average monthly temperature. So it's cold in January, gets warmer in July, and then gets cold again. And it's going to repeat that over and over again. So I'm going to draw myself a graph here. Okay, January 1, we have a temperature of, I'm just going to put 30 here. Okay. We have a high temperature of 84. So my temperature is going to start here. It's going to go up and come back down. If this is January 1 year later, this is going to be 13. Okay. So this one is going to have a phase shift since we are sliding it over 1. And we can do different phase shifts. You could do a positive cosine by using July. I'm just going to use a negative cosine. So this is going to be a negative cosine function. The amplitude. Okay, well the amplitude is going to be the distance from the midline up or the midline down. Or if you think about it, it's going to be half of the range of values here. So I'm going to take 84 minus 30 and divide that value by 2. Okay, so that's 27. So it's 27 from here to here, 27 from here to here. My period, how long does it take to repeat this cycle? Well, if we do this by months, it's going to be 12 months. The vertical shift is going to be our midline, which we can take the 27 and add it to the 30 or subtract it from the 84, or take the average of those two values. Either way, you're going to end up with the same thing, which is 57. And we do have a phase shift of 1. Okay. So my period is 12, so my B is going to be 2 pi over 12, which is pi over 6. We have a phase shift of 1. We haven't done a phase shift yet. But our phase shift formula, remember phase shift equals negative C over B. So in this case, my phase shift is equal to negative C over pi over 6. So I'm going to multiply both sides of this equation by pi over 6, well, negative pi over 6. So I get that my C is equal to negative pi over 6. So let's put all of this together. My function is a negative cosine since we're starting at the minimum. So this is going to be a negative. My amplitude is 27. Cosine pi over 6t minus pi over 6 plus a vertical shift of 57. One more example. The tide in coastal city peaks every 11.6 hours. The tide ranges from 3.9 to 3.3 meters. Suppose there is a high tide at t equals 0. Graph the function and write a function that models the height of the tide at t hours. So my graph, it takes 11.6 to complete a cycle. It goes from 3.3 to 3.9, and we're starting at high tide. Okay, so our function is going to be a positive cosine. My amplitude, again, is going to be half the distance here. So I'm going to take 3.9 minus 3.3, divide that by 2. So 0.6 divided by 2 gives me an amplitude of 0.3. My period is 11.6. So B is going to be 2 pi divided by 11.6. The vertical shift is going to be right in the middle here. So 3.9 plus 3.3 over 2, which is 3.6. So our equation is going to be y equals, it's a positive cosine, so 0.3 cosine 2 pi over 11.6 plus 3.6. So these are just a couple of different scenarios where a sine and cosine curve represents these different situations.